In this video, we are going to cover substitution reactions of alkyl halides. Specifically, we will focus on SN2 reactions. In a substitution reaction, one atom or one group is replaced by another. A group that is being replaced is known as a leaving group. It's labeled here as L, and another group replaces it. In this case, we'll be looking at nucleophilic substitution reactions, which are the most common type of substitution reactions. And so nucleophile is the incoming group that replaces the leaving group. And in fact, both nucleophile and leaving group are actually nucleophiles. It's just that incoming nucleophile is stronger nucleophile than the leaving group. Nucleophilic substitution reactions proceed by different mechanisms, and in this video we are going to examine mechanism of SN2 reaction. SN2 is an abbreviation for the reaction mechanism. Letter S stands for substitution. It indicates that reaction is substitution, replacement of one atom or group by another. Nucleophilic reagent is a nucleophile, and 2 stands for bimolecular. That reaction is bimolecular. In the rate determining step, two molecules or two ions, two particles have to interact, have to collide for reaction to occur. Now you can see that we abbreviate reaction mechanism as SN2, but we actually read it backwards. So reaction mechanism is called bimolecular nucleophilic substitution. So we read 2 first as bimolecular, then N. Note that N is capital but in subscript, nucleophilic, finally substitution. In general terms, an alkyl halide, where halogen is common leaving group, an alkyl halide reacts with a nucleophile to give the reaction product, and halide anion is the leaving group, is suitable leaving group. And so reaction rate depends on the rate constant, of course, and concentration of the alkyl halide in nucleophile. That's what makes reaction bimolecular. That reaction rate depends on concentration of 2 species. Here is one specific example. Reaction of iodomethane with hydroxide, like sodium hydroxide, gives methanol, and iodide anion is the leaving group. So then reaction rate depends on the rate constant and concentration of iodomethane and hydroxide anion. Reaction mechanism of an SN2 reaction is a concerted reaction. Concerted reaction means that reaction proceeds in a single step without any intermediates. So all that there is are starting materials, substrate and reagent. Then as we follow reaction progress, there is transition state. So reactants pass through transition state and finally give products. That's what it means that reaction is concerted. So initially, a nucleophile attacks the substrate from the back side, opposite of the carbon leaving group bond. Carbon is of course sp3 hybridized in the substrate and is attached to halogen. In the transition state, note that carbon atom is sp2 hybridized and forms partial bonds to both nucleophile and the leaving group. This is reaction mechanism of example we already looked at, reaction of hydroxide ion with iodomethane. So in the transition state, carbon makes partial bond with hydroxide and with iodide. And finally, when reaction is completed, carbon-oxygen bond is fully formed and carbon-iodine bond is fully broken, and carbon is again sp3 hybridized. So carbon hybridization goes from sp3 to sp2 in the transition state and back to sp3. And very important feature is backside attack. So nucleophile approaches carbon leaving group bond from the backside. And that's because free electron pair from the nucleophile has to be donated in one of the empty orbitals on the substrate. And lowest energy empty orbital that can accept free electron pair is carbon leaving group empty orbital, carbon leaving group antibonding sigma orbital. In this case, carbon iodine antibonding sigma orbital. And that's the reason for backside attack. That means that nucleophile cannot approach from any other side, any other angle, because there is no suitable orbital to accept electrons from the nucleophile. Now, in the transition state, bond order of carbon is actually 3. So effectively, carbon only makes 3 bonds. And that's because bond order equals number of bonding electrons minus antibonding divided by 2. And so in transition state, nucleophile donates free electron pair into antibonding orbital. So in transition state, carbon acquires 2 antibonding electrons. So when it comes to valence electrons that carbon is surrounded by, there are 6 valence electrons from 3 carbon-hydrogen bonds. There are 2 valence electrons from carbon-iodine bonds. They are still there. Bond is not fully broken. And then there are 2 antibonding electrons from carbon-oxygen bond that is being formed. Or actually, those 2 antibonding electrons are now in the carbon-iodine antibonding orbital. So when we calculate number of electrons, that's 8 bonding minus 2 antibonding, total of 6 divided by 2, 3. So bond order is actually 3. And this animation shows stereochemistry of SN2 reaction, consequence of backside attack of the nucleophile. So leaving group here is shown as red, so leaving atom is shown as red, and incoming nucleophile as green. So you can see as nucleophile approaches, carbon nucleophile bond begins to form and eventually is fully formed, while carbon leaving group first begins to break and eventually is fully broken. And at the bottom, that's followed by the mechanism. You may want to replay this several times to see the reaction clearly. And you can see that stereochemistry actually involves inversion of configuration. So we go from one tetrahedral arrangement to opposite, to what we would call actually a pseudo-enantiomer. Inversion of configuration that occurs in the course of an SN2 reaction is also called Walden inversion, after the Latvian chemist who discovered it and studied it. So this is Paul or Paulus Walden, and this is Walden inversion. So we can see that if starting material is chiral, as for example in case of 2-bromobutane, and then again reaction with hydroxide, if we react one enantiomer, then in the course of reaction, inversion of configuration occurs. You have just seen that incoming nucleophile not only displaces the leaving group, but pushes 3 substituents that don't participate in reaction away from itself to give resulting tetrahedral carbon or tetrahedral arrangement of carbon of the opposite configuration. So if you compare starting material 2-bromobutane and product 2-butanol, they are what we would call pseudo-enantiomers, because they are not enantiomers because obviously they are different compounds. But if you assume that bromine and oxygen are the same, if you were to label them, let's say, as Y, as same substituent, then 2 compounds would have been enantiomers. So one enantiomer would give the opposite enantiomer. So we say that reaction occurs with inversion of configuration. And this is often pictorially represented as inversion of an umbrella in a wind. So if you imagine somebody walking with an umbrella in a wind, and then gust of the wind will force an umbrella first through transition state, through flat configuration, to being completely inverted. So that's one way to memorize or imagine inversion of configuration that occurs in the course of an SN2 reaction. Now let's consider what happens in the course of reaction, how the inversion affects configuration of the product. So here is starting material. We can see that leaving group has highest priority, priority 1, and then remaining substituents have priority as indicated. So they are not any particular substituents, they are indicated only by different colors. So substituent with priorities 2, yellow, 3, blue, and 4, purple. Incoming nucleophile will also have priority 1. That means once it's incorporated into the molecule, instead of the leaving group, it's going to have higher priority than any of the existing substituents, any of the substituents labeled as priorities 2, 3, or 4. So if starting material is an S enantiomer, and you can see this one is S enantiomer, then as reaction occurs, product is R enantiomer. And so that's the result of inversion of configuration. If priorities remain the same, priorities of the substituents remain the same, then S enantiomer is converted into R enantiomer. R, of course, conversely would be converted into S enantiomer. But don't assume that that's always the case, that in every case R enantiomer is converted into S, S into R. That one enantiomer, the designation is always the opposite. That's the case only if priorities remain the same. Let's see now what happens if priorities are not the same. So what happens now if leaving group is still highest priority, priority 1, but incoming substituent will have priority 2. So one of the remaining substituents that now has priority 2, will become substituent with priority 1. An incoming substituent will become substituent of second highest priority, priority 2. So now we have S enantiomer as a starting material, but after reaction is completed, now yellow substituent becomes priority 1 substituent, while incoming substituent is priority 2. And now, even though inversion of configuration has occurred, S enantiomer gives S product. So for that reason, never make an assumption about configuration of the product, designation of configuration of the product, R or S. It's going to be particular designation based on what was the starting material. Always check what the priorities of the substituents are, whether they remain the same or not, and whether you have to determine priorities again and then determine configuration of the product again. And here is how we represent inversion of configuration. First by perspective formulas. So S2 bromobutane reacting with sodium hydroxide. So bromine is replaced by hydroxide, bromide by hydroxide. So substituent with priority 1, bromine, is replaced by substituent with priority 1, oxygen or OH group. In that case, S2 bromobutane gives R2 butanol. And of course, if starting material were R2 bromobutane, product would have been S2 butanol. So, and you can see how we represent two products. They look like enantiomers, except that leaving group and incoming nucleophile are different. And here is how we represent the same reaction with Fischer projections. So again, they look like two enantiomers, except that nucleophile and the leaving group are different. SN2 reactions have a lot of application in organic synthesis, in synthesis of organic compounds, conversion of one compound into the other. SN2 reactions are very important because they are one of the most important methods to accomplish functional group interconversions, or so-called functional group transformations. We abbreviate that as FGIs. So conversion of one functional group into the other. In organic chemistry, in general, we have two types of reactions. One type is to form new carbon-carbon reactions to establish skeleton of the molecule. And another type is functional group interconversions, to convert one functional group into the other. And so we carry out these two types of reactions in sequence until we end up with desired products. So these reactions here listed are some of the most common SN2 reactions. You may want to pause video here and examine them in detail. So you can see that alkyl halides with reasonably good leaving group, chlorine, bromine, or iodine, readily react with variety of nucleophiles to give corresponding products. They also react with carbon nucleophiles, particularly sp carbon nucleophiles, to form new carbon-carbon bonds. So SN2 reactions could also be used in forming of carbon skeleton, because they are suitable methods to form new carbon-carbon bonds. And finally, they could be used to replace halogen with hydride nucleophile, with H-. But hydride nucleophile itself, in form of, let's say, sodium hydride or lithium hydride or calcium hydride, those typical metal hydrides, is not suitable. That one would react as a base rather than a nucleophile. For hydride to be a nucleophile, to act as a nucleophile, we need complex metal hydrides. And the most commonly used complex metal hydrides are sodium borohydride, NaBH4, and one shown here, lithium aluminum hydride, LiLaH4. So they act as H- as hydride nucleophile and displace halogen with hydrogen. While most of the SN2 reactions go to completion, simply stronger nucleophile is the reagent and displaces the weaker nucleophile, the leaving group, and so reaction goes to completion. Sometimes an equilibrium is established, and so we have equilibrium mixture where reaction is only partially complete, and then we have dynamic equilibrium, so concentrations of the starting material product no longer change. That's particularly the case if we carry out halogen exchange reaction, if we want to exchange one halogen with another. And most commonly, we want to replace chlorine or bromine with iodine, because iodine is the best leaving group. So we may want to replace chlorine or bromine with iodine. But to avoid formation of an equilibrium, we apply Letelier's principle. Hopefully you recall Letelier's principle from general chemistry course. So if you consider an equilibrium reaction, let's say reaction of bromoethane with iodide, like sodium iodide, then product would be iodoethane and sodium bromide. But that would be a dynamic equilibrium. Although iodoethane would predominate, still we would have a mixture of the two compounds. So to shift equilibrium to the right, we can consider expression for equilibrium constant in general terms. So it's multiple of concentration of products divided by multiple of concentration of reactants. We can shift equilibrium to the right, either by using one of the reactants in excess. So in this case, for example, we can use sodium iodide in large excess, but that would be wasteful. Or we can remove one of the reaction products. So if we can remove one of the products out of the equilibrium, that would be the best. And in this case, we can remove sodium bromide. We can do so by carrying out reaction in acetone as the solvent. Because if reaction is carried out in acetone as the solvent, sodium iodide is one of the few salts, inorganic salts, that is soluble in acetone. But sodium bromide and sodium chloride are not. So as we carry out reaction, sodium iodide, which is soluble, will be used up, and as sodium bromide is formed as reaction product, it will precipitate out of the reaction. And of course, equilibrium will keep on shifting to the right, because as sodium bromide is taken out of the equilibrium by precipitation, remember, only species that are present in the solution are part of the equilibrium. Anything that precipitates or evolves as a gas leaves the equilibrium and therefore participates or helps shift equilibrium towards products. So in this case, sodium bromide keeps precipitating and equilibrium keeps on shifting to the right to form more and more sodium bromide until eventually reaction is completed. So remember these reaction conditions. So a reaction of an alkyl halide, alkyl chloride or bromide with sodium iodide in acetone is always an SN2 reaction and always goes to completion. This completes our examination of SN2 reactions, mechanism and some uses, and next we are going to look at factors that affect rates of SN2 reactions.